As with various topics in A2, when it comes to your second year and you're looking at these same concepts from first year, such as integration, you may find that the questions are now getting a bit more difficult, a bit more complex, and the base methods that you learnt when you were introduced to these concepts may not perfectly work anymore. So we'll need to employ something else. For integration, one of these alternative methods is integration by substitution, where we're going to replace terms within the current integration with ones that are simpler, so long as we then switch them back afterwards, if that is necessary. Let's take this integration here. So we need to integrate x squared over x cubed plus 1. Now, yeah, as it stands, we may not be entirely sure what to do with this. What we can do is these steps down here. So first of all, we need a u expression. Strictly speaking, it could be any letter you wanted, but u is the traditional one. U equals some part of this expression that we want to switch it out for. In the event of a fraction, it's usually the denominator, and in fact also usually the question will probably specify what substitution you're going to make. Just to also clarify for you that it is indeed a substitution question. Yep, so in this case we'll say u equals x cubed plus 1. Now with this u expression, we're going to differentiate it and then rearrange to swap out dx for du. So if we were to differentiate this, first of all it would be du over dx, because we're changing u with respect to a change in x. Just differentiate as you usually would. So coefficient times power, well 1 times 3 is going to be 3, and then drop the power by 1, you get 2, and the 1 disappears because this is currently like x to the 0, so coefficient times power is 1 times 0, 0 goes away. With this then, we can just swap it around slightly so that you have du equals 3x squared dx. Almost there. But actually in this case, I'm going to do one other thing, which is to move that 3 over to the left-hand side, making this a third, and du is x squared and dx. Now the reason for this, and the reason why we're differentiating and swapping out to begin with, is because if we're going to be changing these x's into u's, we can't be integrating with respect to x anymore. We'll have to integrate with respect to u. We need to turn the dx into a du, and it's not always guaranteed to just be an easy swap. So, we'll notice this is x squared and this is dx, this is x squared and this is dx. So therefore, when we switch out the dx for a du, you're going to swap out both of these together, leaving you with just 1 over x cubed plus 1, and this will be then multiplied by a third with then du afterwards. If you want, whenever you have this kind of like coefficient or a fraction that's being times by it, you can bring this out in front of the integral sign, so long as you remember to times it back afterwards. It won't actually make a difference to the final value. So bring the third out front. Then here we can make this 1 over u. We're now going to do the main substitution, switch out this denominator for that value of u. Just the reason I suggest not doing this first and doing the differentiating first is sometimes you'll find that with this like du and dx expressions, that actually gets rid of the denominator for you. So if you've already switched out for u, you're going to get into a little complication. Switch out this first, and then only if this phrase still remains, then do you do the main substitution, as in this case. Either way, we now have a third of the integral of 1 over u du, and if we're not familiar, 1 over u is going to integrate to be ln u, because as it stands right now, you could call this u to the power of minus 1, and if you were to add 1 to the power, that would become 0. Yet if you then divide by that new power, well, you can't divide by 0, that would break the equation. So we use a natural logarithm instead. If you're not familiar with natural logarithms, I suggest that you watch the videos on like logs and exponentials. So we've got now a third of the integral, which was the ln u, plus c, because it's an indefinite integral. And then we just need to times out the brackets. In this case, because there's only a single term in there, that's just going to be a third ln u, still plus c. We've ignored these steps here just because there wasn't any x left over and there are no bounds. So yeah, we've just integrated. And now substitute back for x if necessary. If it's an indefinite integral, yes, you want to switch back. I'll explain in the example on the right what we do if it's a definite. But for now, yeah, third ln, and instead of u, we'll turn that back into x cubed plus 1, still plus c afterwards. So there you go. The integration of this expression here, this fraction, would be this. Following these same steps then, let's give that example of a definite integral, as well as an example which now also involves e to the x. Again, if you're not familiar with that, go to the exponentials and logs. Here, we again need to first of all create a u expression. It's probably going to be the denominator. So we'll say that u equals 1 plus e to the x. Now, when you differentiate this, if we recall from the exponential stuff, e to the x doesn't change when you differentiate it. So the 1 will disappear for the same reason that the 1 disappeared over here, and this then just becomes e to the x. So du equals e to the x dx. Now, when we switch this out, obviously we can take out the dx here, and we can take out a single e to the x from the numerator. However, that hasn't completely got rid of the numerator. What we're left with, so still between these bounds of 3 and 2, is going to be e to the 2x still, and plus 1 plus e to the x, and then that then just becomes your du. At this point then, yeah, we could switch out this denominator to just become a u, so e to the 2x over u du, but we now have x terms still remaining. We've already done the main substitution though, we've already switched out the du dx, so we just have to rearrange this u expression again to get rid of this last thing. So just bringing this down here. If you minus the 1 over, you get u minus 1 equals e to the x. How then do you get e to the 2x? Well, e to the 2x, if you like, is e to the x squared. Because if you power bracket power, that times them together. Yeah, so this is the same as this. If this is e to the x squared, then this will be u minus 1 squared, making this substitution here. So on the top we now have u minus 1 squared, on the bottom is a u du, and this is going to be the same as integrating between 3 and 2, u squared minus 2u plus 1, which is going to be over that u from before, du. And if we just simplify these, dividing each term each time, so between 3 and 2, u squared divided by u is just u, minus 2u divided by u is just minus 2, and then you still have 1 over u from before. Now, while we now have something that we could integrate, its individual terms, they're pretty straightforward, we still need to change the bounds. We have to take into account this here. If there are bounds, convert from x to u. What I mean by this is to say, well, we'll take our u expression one more time and go 1 plus e, and then to say the upper bound is 3. And you work out what that is, and u equals 1 plus e to the 2. Because right now there's 3 and the 2, that's what x is between, that's not what u is between. They would be different curves if you were to try to plot them, so they're going to have different bounds representing the same ultimate value, the ultimate area. Now usually, if this was this kind of question like we have on the left, where you just have like x cubed plus 1, plugging in an x value, getting out of u, that would be fine. It's going to be a pretty nice number. Here, because we're working with e's to powers of x, we're going to have decimals. We're inherently going to have to round. Now that's fine, and well, ideally you'll try to keep it as accurate as you can in your calculator. But we may want to shift back to x at a later point, and I'll explain what I mean by that when we do it. If we were to go down this path though, let's just say to 2 decimal places, you would end up with the upper bound becoming 21.09 and the lower bound being 8.39. So that's what we're going to have in our integral, therefore, for these bounds, 21.09 and 8.39. When we integrate then, if we're going to keep it in terms of u, you end up with a half u squared, because you can raise the power by 1 to make it 2 and divide by that new power. The minus 2 becomes minus 2u, and as we had on the left here, 1 over u is going to become ln u. And because we're still in terms of u, we're still going to be between these bounds of 21.09 and 8.39. However, if you would prefer not to now be substituting with these decimals, because this would then become like half 21.09 squared minus 2, 21.09 and so forth, then you have to do it again with the 8.39. If you prefer not to do that, we can just substitute now back into x like we did do over here. It's not as optional here, because if you are keeping the u bounds, because that will account for everything. But if you want to shift back to x, then now becomes a half of 1 plus e to the x from the substitution above, squared, minus 2, 1 plus e to the x, plus ln, 1 plus e to the x, and close bracket. And that's now back between the bounds of 3 and 2. If you're intending to do this, then you don't necessarily have to work out these here. Thus, you end up with the likes of a half 1 plus e to the 3 squared plus, minus either way, and so forth, and that will keep on going. Now, if we notice actually, 1 plus e to the 3 is the same as the 21.09. So either way, we actually have these same values in the brackets, hence it doesn't matter. What matters is once you've filled this all in your calculator and plugged it all in, let's say keep to 2 decimal places, you should get a final answer of 162.64. If we can see the steps that we've done here, how we've followed these different statements here to get a u expression that we're going to substitute for, how we've differentiated, and once you've done all that, integrated. If we're happy with all that and want to have a go for ourselves, let's just see if you can apply those principles to another question that once again looks at crossing over with another concept from the A level. So, what if this time we had the integral between 0.5 and 0 of 1 over the square root of 1 minus x squared dx, and this time the question is specifying that you use the substitution x equals sine u. So just looking at this, it may not appear immediately obvious that you would be using such a thing, but the question's told you, so you will. Try to see how you can apply these steps to this here. You are going to have to think about how you can differentiate a sine and cos function. If needs be, such things can be recapped in the differentiation videos relating to trigonometry. And if you're okay with how you might go about that, pause the video, have a go just working it through, and then press play again when you're ready to compare. Okay, now immediately this is slightly different to the previous question, because here x is the subject rather than the u. In this case, I would not advise immediately trying to make u the subject, because that's going to involve having a sine inverse x, and then differentiating sine inverse is going to be even more complicated. So instead, I would suggest just differentiate it as is. This means dx is on the top and du is on the bottom because you're changing x with respect to u, and sine differentiates to cos. Thus, if we now times that around, you have dx equals cos u du. Substituting this into here, you end up with, so again, integral between 0.5 and 0, and 1 over square root of 1 minus x squared. This is now times by cos u and ending with du. Next, because we still have this denominator, we'll make the substitution. So between 0.5 and 0, this is now 1 over the square root of 1 minus. Now, if x is sine u, x squared will be sine squared u du. Oh, well, actually, yeah, at this point we might as well just put the cos u on top. Because it's multiplied, it would be the equivalent of being on the numerator anyway. Now, if we think to our trigonomic identities, we can simplify what's underneath the square root. 1 minus sine squared is the same as cos squared, because sine squared plus cos squared equals 1. So this is going to be the same, once again with these bounds, of cos u over the square root of cos squared u du. Now we may be noticing that something is starting to happen, but we'll follow it through anyway just to make sure. So between your 0.5 and your 0, the square root of cos squared is just going to be cos. So you have cos u over cos u du, but cos cancels with cos, meaning this is just the integration of 1 du. Now, in this case, we still need to change the bounds because we are still in terms of u, even though it just looks like a 1. So if we just say over here, say that now we are going to have to do the inverse. So u is the sine inverse of x. Initially, that's going to be 0.5. See what that equals. And then it's also going to be the inverse of when it's 0. Because it's 0.5 and 0, there's no suggestion of pi. We're just going to make sure we're in degrees rather than radians. So if you do the sine inverse of 0.5, you get 30, and the sine inverse of 0 is just 0. So in fact, these bounds here, that's going to stay 0 on the bottom, but on the top here, this becomes 30. Now, when we integrate this, the integration of 1 is just going to be u, because we're with respect to u. Between 30 and 0 is rather simple. We're just going to say, well, to do it thoroughly, 30 minus 0, so that would just be 30. If we're good with that, we can just see how that worked, how we can employ trigonometry and differentiation into this integration topic. Let's just round off by looking at a proper question. Use the substitution x equals 4 sine squared theta to show that the integral between 3 and 0 of the square root of x over 4 minus x dx is the same as lambda of the integral between pi over 3 and 0 of sine squared theta d theta, where lambda is a constant to be determined. Now, obviously, we're using slightly different notation here. We're using theta instead of u. We've got this lambda that we need to work out, but again, that's just a number that will come from the regular working. So, all the same, it'll be the same steps as we were doing previously. We'll just write out the substitution expression again, just so we have it. So, x equals 4 sine squared theta. If we're going to differentiate this, I say we'll just keep the fact that x is already the subject. Don't try to do any kind of inverse thing. And because it's obviously first on the left, it will go on top. When you are differentiating this 4 sine squared theta, you're going to have to use the chain rule, okay, which you're not familiar with if you find a video on it. But basically, we're first of all going to think of this instead as 4 bracket sine theta and squared on the outside, just to help with the visualizing of the representation for the chain rule. What we'll then say is it's the coefficient times the power, as you usually would do when you're differentiating. So it's going to be 8. Then you have what's inside the bracket as before, and here, because we've dropped the power by 1, that's now just 1, so sine theta. But then you also times by the differential of what's in the bracket, and sine theta differentiated is cos theta. So dx over d theta is 8 sine theta cos theta. So dx equals 8 sine theta cos theta d theta. When we make this initial substitution, then we can say that we are between 3 and 0 under the square root of x minus over 4 minus x, just make it excessive, and then this is being times by 8 sine theta cos theta d theta. Next, because these expressions still exist, we can make the main substitution. So we'll have between 3 and 0, Now the square root of 4 sine squared theta over 4 minus 4 sine squared theta times 8 sine theta cos theta. Now, what we can do at this point is cancel through by a factor of 4, leaving us with just a 1 here. So I just rewrite it up here, 3, 0, square root of sine squared theta over 1 minus sine squared theta. 1 minus sine squared theta you can rewrite again using trigonomic identities as cos squared theta. So we now got between 3 and 0. We have the square root of sine squared theta over cos squared theta, still times by this 8 sine theta cos theta. And then to square root, because both the top and bottom are squares, it will just get rid of them. So between 3 and 0, you've now just got sine theta over cos theta times 8 sine theta cos theta d theta. Once again, we now actually have something that cancels. The divide by cos theta cancels with the times cos theta, and the sine times the sine will become sine squared. So I'll leave the bounds blank for just a second. We'll have 8 sine squared theta d theta, and the reason I left the bounds blank is because we now have to change them. The question here is telling us we're going to be in terms of pi, so we do want to be in radians. For this rewriting of the bounds here, if I just bring that expression down here, what we'll end up with is x over 4 square rooted, and then this equals sine theta. So theta is going to be the sine inverse of the square root, and we'll do it with each one. So 3 over 4, or square root of 0 over 4. If you plug these into your calculator and make sure in radians, surprise, surprise, you end up with pi over 3 and 0. So yeah, just to confirm, those are the bounds we're going to have here. And thus, this 8 here equals the lambda, because since it's a coefficient, they can just bring it on the outside. So long as it times back afterwards, it doesn't matter. All right. Now that we have this, use integration to find, well, that integral, giving it answers in the form of a, I believe that's meant to be a pi rather than n, so a pi plus b, where a plus b are exact constants. Well, now that we are in this form, we are going to have to integrate. The issue comes, though, with integrating sine squared theta. Now, there are a couple of ways of doing this, but there's one way in particular that the mark scheme is expecting you to use. There's a specific identity, which is based around the double angle formula. If I just do it down here. So the idea that cos 2 theta equals cos squared theta minus sine squared theta. If we were to just start rearranging this, like bring the sine squared onto the left to make it positive, and then you have cos squared theta minus cos 2 theta. This cos squared can be rewritten as 1 minus sine squared theta, so minus cos 2 theta. Add this over, you end up with 2 sine squared theta equals 1 minus cos 2 theta, and thus sine squared theta equals a half of 1 minus cos 2 theta. They are expecting you to be just familiar with how you can use this. Even though it's not explicitly given in a formula book or something, it's a method of deriving or manipulating the double angle formula to get something in terms of squared. You could have done the same to make it cos squared theta. The point is, though, over here, if we've brought the 8 onto the outside, we can then say that that's pi over 3, 0, and then sine squared theta d theta. Instead of this, you can actually just write it as your or this expression down here, the half of 1 minus cos 2 theta. Because the half is a coefficient, you can bring it out here as well. So that's 8 times a half here with the point. So that gives you a 4. If we do now integrate this, so you have 4 and the brackets, 1 integrating with respect to theta is just going to become theta. For cos, minus cos is going to integrate to minus sine, but also you need to divide by the derivative of what's in the brackets. 2 theta divided by, differentiated is just 2. So you end up with minus sine theta over 2, or minus a half sine 2 theta. If you're not familiar with that, once again, I'll just say look back on differentiating the sine and cos functions. Okay, so in between these bounds, so what you're going to end up with is 4 lots of pi over 3 minus, so 4 times a half is 2, so 2 sine 2 pi over 3, and then that's going to have minus from it, so 4 times 0 minus 2 sine 2 0. Depending on your calculator may not give the answer to you in terms of pi, which is what the answer's asking for. So you may just have to do this manually. Here, this will be 4 pi over 3. This here, just putting it into your calculator, make sure in radians, that's going to get you minus root 3. And actually, this entire bracket here, 4 times 0 is obviously 0, and 2 sine of 2 times 0 is also going to be 0. So really, we're actually taking nothing away, leaving you then with just this expression. Therefore, comparing to this form, A is 4 over 3, and B is minus root